All right, it's our last topic for Unit 3. It's quite short, and I think they left the easiest for last, higher order derivatives. So we've been finding first derivatives. Like, if you have f of x, what is the derivative of x, right? So what is the slope of the tangent line at certain points? But you can also find the second derivative, the third derivative. You can find the 1/1,000,000th derivative, right? So the way you didn't note that is if you're finding the second derivative, it has two apostrophes, so f double prime of x. Or you could say d squared y over dx squared, or sometimes you see it like this, right? These are just the different ways to show it. You can compare it to the first derivative. So that literally means what is the slope of the slope of the slope, right? The rate of change of the rate of change, right? And we'll talk about what that means. So it's the same thing. You do the same thing. You take the derivative of the derivative, but it's just a lot more to keep track of. And the reason we do these is because there's applications for it. So I'm going to show you the application. So here's example 1. The position function for objects falling on the moon, where there is no atmosphere and thus no air resistance, is given by the position function s of t equals negative 0.81 t squared plus 2, where s of t is the height in meters and t is the time in seconds. What is the acceleration of the object on the moon? Right, so this is the application. If the original function s of t gives you what? The distance or the height. If you took the first derivative of the position function, the rate of change of distance, right? Well, the rate of change for distance over time is just the velocity function, right? So the first derivative gives you the velocity. Well, what if you take the derivative of the velocity function, the rate of change of the velocity? Well, that gives you the acceleration, right? So this is why we have these things, because they're applications. So if you have a distance function and you take the first derivative, you get the velocity function. You take the derivative of the velocity function, you get the acceleration function, which is the second derivative of the distance function. So they're asking us here to find the acceleration. So they're asking us to find the second derivative. Okay, so first let's find the first derivative, which means the velocity function, right? Okay, so the first derivative of this would be negative 2 times 0.81 is negative 1.62. Oops, 1.62, and then times t, and then that plus 2 just goes away to plus 0. Okay, and this is in what? Meters and seconds. So the velocity function is meters per second. Okay, they're asking us for acceleration. So we can find the second derivative of t, which is going to give us the acceleration function. So what is the second derivative of t? Well, I'm going to take the derivative of the first derivative. So if I take the derivative of negative 1.62 times t, I just end up with negative 1.62. And it's acceleration, so it's meters per second squared. So that's the answer right there. The acceleration of this object is constant. It's falling at negative 1.62 meters per second squared. Okay, now let's go away from a context to just finding some second derivatives. So if f equals 4 times x to the negative 3 halves, what would the second derivative be? Well, the first derivative would be what? Negative 3 halves times 4 times x. Negative 3 halves minus 1 is negative 5 halves. So f prime equals, what is this? Negative 12 divided by 2, so negative 6x to the negative 5 over 2. Okay, so then the second derivative would be, take that down again, negative 6 times negative 5 over 2 is going to be 30 over 2. That comes out to 15x. And then negative 5 halves minus 1 becomes negative 7 halves. So that's the second derivative. Right here, let's find the second derivative. Well, what I need to do the quotient rule here. So u equals x, v equals x minus 1, u prime equals 1, v prime equals 1. So the derivative of this thing is u prime v, so x minus 1, minus uv prime, so minus x, all over x minus 1 squared. So I can see that that simplifies so that f prime of x just equals minus 1 over x minus 1 squared. Okay, so if I have to find the second derivative, I have to find the derivative of this function, I could actually rewrite f prime of x like this, couldn't I? Right? So, because I don't want to use the quotient rule again, I'm trying to avoid that. So to find the second derivative, take the negative 2 down, that becomes 2. X minus 1 times negative 3, right? That is the derivative of the outer function, but I need to use the chain rule. So derivative of the inner function, x minus 1, well, that's just 1. So I really didn't need to, if I forgot the chain rule in that second, I would have gotten the right answer, but by chance. So this is the second derivative here. Did I do something wrong? Negative 2. No, I didn't. I just forgot to write my negative here. Okay, now here. C. Well, the first derivative, I have to use the product rule, right? So u equals x, v equals sine x, u prime equals 1, v prime equals cos x. Okay, so f prime of x equals x times cosine of x plus 1 times sine of x. All right, now let's find the second derivative. I'm going to have to do another product rule here, right? So for this, I'm going to write u equals x, v equals cos x, u prime equals 1, v prime equals negative sine x. So the derivative here would be negative x sine x plus cos x. All of this plus what's the derivative of sine x is cos x. So f double prime of x equals what? Negative x sine x plus 2 cosine x. Okay, now let's do a little bit more practice here. An object moving along a horizontal coordinate line, so a position function, t cubed minus 6t squared, s is the directed distance from origin in feet, t is the time in seconds. What are the velocity and acceleration functions? So I'm just going to start with 1a here. So we know the position function is t cubed minus 6t squared. So the velocity function is just the first derivative. What is that going to be? 3t squared minus 12t. Okay, and the acceleration function is just going to be the derivative of the velocity function, which would mean it's the second derivative of the position function, would be what? 6t minus 12. Okay, so we did A. And now B says, when is the object moving to the right? Well, the object is moving to the right when the velocity is positive. So when is the velocity greater than 0? Well, when is 3t squared minus 12t greater than 0? Right, so, well, I can factor this out, and I end up with t minus 4 has to be greater than 0. So we know that divided by 3t, t has to be greater than 4 seconds for the velocity to be positive. Okay, C. C says, when is the object moving to the left? Well, the object is moving to the left when the velocity is negative. Well, when is it going to be negative? When it's not positive. So that's when t is less than 4 seconds, right? I'm just using what I did in B. So you can really be thinking of this if this is a object moving on a horizontal coordinate plane. Here is when t equals 4 seconds, right? So what's happening here is that when you're less than 4 seconds, the velocity is less than 0, and here the velocity is greater than 0. So if you're thinking about it, actually let's do D first before we do that. So D is saying, when is the acceleration negative? Okay, so when is A of t less than 0? When is 6t minus 12 less than 0? Well, that is when 6t is less than 12. That is when t is less than 2. So if you're thinking about when t equals 4 seconds, how far away from the origin is it at 4 seconds? So if I come and plug 4 up into the position function, I end up with 4 cubed minus 6t squared. Do I have my calculator? Yes, here. So 4 cubed minus 6 times 16. So it's 32, what is this, feet away from the origin, right? So it's at negative, this corresponds with a distance of negative 32 feet, right? So if I'm thinking about that, let's plot that. Here's 0. Here's negative 32 feet away from 0. So what's happening at time equals 0, when t is less than 0, or when t is less than 4 seconds, what happens? It's moving to the left. So it's moving to the left, and then 4 seconds pass and it turns around, right? And it starts moving in the positive direction. That's what we have. This happens when t equals 4 seconds. That turnaround point. All right, 2. F prime of x equals x squared. What is f double prime of x? Okay, well, that one's not too bad. Why do I even have that here? That's 2x. That's so easy, right? I'm just taking the derivative of that one. That one's too easy to have on this practice sheet. Okay, so if f double prime of x equals 2 minus 2 over x, what's f triple prime of x? Okay, let's take the derivative of this. What's the derivative of 2? 0. I'm going to rewrite this as minus 2 times x to the minus 1. Because I don't want to use the quotient rule right now. My brain hurts too much. So that would become positive 2 x, and then that would be negative 2, right? So f triple prime of x equals to 2 over x squared. All right, 4. Another word problem. It says an automobile's velocity starting from rest is v of t equals 100 over 2t plus 15, where v is measured in feet per second. Find the acceleration at 5 seconds, 10 seconds, and 15 seconds. Okay, so we have to find the acceleration, which means we have to find the derivative of the velocity function. All right, quotient rule. U equals 100, v equals 2t plus 15, u prime equals 0, v prime equals 2. So the acceleration equals u prime v, well that's 0, minus v prime u, well that's 200, all over v squared, so 2t plus 15 squared. So that equals negative 200 over 2t plus 15 squared. There's our acceleration functions. Now let's evaluate at these times they gave us. When t equals 5, I would end up with negative 200 over 2 times 5 is 10, so 10 plus 15 is 25 squared. When t equals 10, I would end up with negative 200 over 2 times 10 is 20, 20 plus 15 is 35 squared. And when t equals 15, I would end up with negative 200 over 2 times 15 is 30. 30 plus 15 is 45 squared. Right? And I could evaluate all of these. I'm not going to put it in my calculator. But one thing I'm definitely noticing is that the velocity, I'm sorry, the acceleration is always negative at all of these points, right? And you can put those in your calculator and figure out the decimals if you needed to. But I'm not going to do that right now. Okay, last lesson for Unit 3. Woohoo, we're done. See you guys later.